This presentation is delivered by the Stanford Center for Professional Development.
Okay, all right. Let's, if you can go down, we'll talk about complementary slackness. By the way, the topics we're covering right now involving duality, full optimality conditions, things like that, these are very tricky. So you actually have to go over these a couple of times to get the exact logic of what implies what. It is quite tricky. So just to let you know, actually I read this stuff very carefully a couple of times, actually, just so I can remember sort of exactly what implies what, because it's kind of subtle. Okay. And let's see if I can end up not confusing myself today. Okay, so assume strong duality holds. Now what that means is we have a primal optimal point, x star, and we have lambda star, nu star, which are dual optimal. Okay, and these are just any primal optimal, any dual optimal point. And of course, what it means for strong duality, it just means that the value achieved by x star, which is feasible, is equal to g of lambda star nu star. Now that's a lower bound on the optimal value. So if you've got a point that's feasible and has an objective value equal to the lower bound, you're done. And it's optimal. So you can think of lambda star nu star as a certificate proving x star is optimal. And by the way, the same is true the other way around. X star is a primal certificate proving lambda star nu star are optimal. Okay, so let's see what this means. G star of lambda star nu star is, by definition, it's the infimum over of this thing. I know we went over this last time, but I just want to sort of go over this again quickly. This is the infimum over x, over all x here, of this Lagrange, of the Lagrangian. Now, of course, that has to be less than or equal to the value of the Lagrangian if you plug in x star. You plug that in and you get this. But x star is feasible. But therefore, fi of x star is less than or equal to 0. The lambda I stars are bigger than or equal to 0. They have to be. That's dual feasibility. So this whole term is less than or equal to 0. This term is equal to 0 because these hi's are 0. Therefore, this thing here is less than or equal to that because it's this thing here plus 0 plus something less than or equal to 0. So it's less than that. Therefore, everything in between this chain has to be equal. Every expression, because it's something is blah, 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 less than this, less than that, back to something again. Everything in between has to be equal. And that tells us, since that's 0, it says this thing's got to be 0. Now that's a sum of a product of non-negative numbers with non-positive numbers. And that 0, that happens only if every single product is 0. Okay? Now, by the way, today this will make sense. Last time it was just an algebraic fact. Today, there'll be lots of interpretations under which this makes sense. What that says is the following. For each constraint, either lambda I star is 0, so either the optimal Lagrange multiplier is 0, or the constraint is tight. That's what fi of x star equals 0 means. So you're either tight or the constraint is 0. And you can twist the logic around and say it in many other ways. You could say things like this. You know, if lambda I star is positive, then the constraint is tight. If the constraint is slack, that means fi of x is less than 0, then you must have lambda I star equals 0. Okay? And later today we're going to have some interpretations of lambda I star that will make this completely clear and totally intuitive. So this is called complementary slackness, and what it really means is that the vector of these f's and the vector of the lambdas actually have complementary sparsity patterns. So a sparsity pattern in a vector tells you what entries are 0 and what are non-zero. And this says they're complementary. They cannot have non-zeros in the same entry. So that's the picture. Okay. This brings us to something called the KKT conditions. There's some fun history here. Kuhn and Tucker are sort of well known, who had worked these out at some point. I mean, these are kind of silly because I think for sure there were people in Moscow, for example, who knew these earlier, but it doesn't matter. And then actually somebody uncovered a 1938 master's thesis by this poor guy Karush. It had everything in it. So, and actually miraculously they added his name to this. So these are now in the West it's called the KKT conditions. So this is basically a generalization of the very simple fact that for an unconstrained problem, the necessary and sufficient conditions for optimality for a convex function is that the gradient is 0. That's it, period. You already know that. Now the question is, what about with inequality constraints and so on? And this is for differentiable fi and hi. Okay, here it is. So here it is. This is, you have to have the following. Obviously, you have to have primal feasibility. So x could not possibly, by definition, it could not be optimal if it weren't feasible. So feasible means that it satisfies the inequality constraints and the equality constraints. That's feasible, number one. Dual constraint, dual feasibility says that the lambda i's are bigger than or equal to 0. Complementary slackness says lambda I fi is 0. And then the final one is gradient of the Lagrangian with respect to x vanishes. That's this expression here. So this is simply, you might write this something like this, partial L, partial x, something like that. That's a gradient. I guess maybe I'll write it this way. Gradient xl equals 0. Okay? So these four conditions together are called the KKT conditions. And in fact, what we just showed is the following. If you have a problem, by the way, convex or not, either way, and strong duality holds, then the KKT conditions will hold for any pair of a primal and a dual feasible, a primal optimal and a dual optimal pair. You had a question? Oh, okay, sorry. Okay, so that's the, so if strong duality holds, the KKT conditions must hold. Okay? Now, for convex problems, it's necessary, and it's sort of necessary and sufficient, and you have to get sort of the logic exactly right. So let's see what that means. Now suppose you have a convex problem and some points, x tilde, lambda tilde, and nu tilde satisfy KKT. Okay? I'm writing them as tildes because if I put a star on them, it sort of presupposes by the notation, it implies that they are optimal. They will turn out to be optimal, but so right now I'm going to use tildes which are more neutral. Okay? So suppose now x tilde, lambda tilde, nu tilde satisfy the KKT conditions. Then we're going to argue that in fact they're optimal. Okay? X is primal optimal, lambda nu is dual optimal. Okay, so the way that works is this. From complementary slackness, if complementary slackness holds, if the KKT, if all of these conditions hold, then in fact lambda I fi is 0, right? Because for each I, either lambda I is 0 or fi is 0. Okay, these are all the other things. The nu I, hi, those are all 0, and therefore L of x tilde, lambda tilde, nu tilde is equal to f0 of x tilde. Okay, so we'll start with that. Now the fourth condition, that's this gradient condition here. If this holds, then look at this. f0 plus lambda, some lambda I fi plus some nu I hi is going to be a convex function. Why? Because the hi's are affine. You can multiply them by any number and still have an affine function. The fi's are convex. I can multiply them by any non-negative numbers, still get a convex function. I can add up a bunch of convex functions to get a convex function, differentiable. This condition says that the convex function f0 of x plus some lambda I fi plus some nu I hi, that this thing has a gradient that vanishes. If that has a gradient that vanishes, it's a convex differentiable function, then at that point is the minimal. Therefore, that says that x tilde here minimizes, is a minimizer of the Lagrangian. And therefore, if I evaluate L of x tilde, lambda tilde, nu tilde, I get G. Hey, I'm done. Because now I've just shown that these two are equal. That's an objective, that's obviously an upper bound on the optimal value. That's a lower bound. They're equal. It's optimal. Okay? Now, there's also the question of how Slater's condition comes in. So let's review what we've seen. We've seen the following. If, for any problem, convex or not, you have strong duality obtains. If that's the case, then the KKT conditions hold. Okay? The converse is false. Actually, in other courses, not this one, you'd study that like crazy, and you'd have numerical methods that would search for KKT points, and there'd be false KKT points, KKT points that aren't optimal and so on. But as far as we're concerned, any problem, you have strong duality, KKT conditions hold. That's number one. Number two, if the KKT conditions hold for a convex problem, you have then those points are a primal, dual, optimal pair, period. Okay? And the last one says this. You have to have Slater's condition. Slater's condition says that if Slater's condition is satisfied, that means there's a strictly feasible point. There exists a strictly feasible point. Then it says the following. It says that a point is optimal if and only if there exists lambda nu that satisfy KKT conditions. So that's that's the full logic of it. Is there a question?
When you say KKT conditions, do you mean there's necessary and sufficient?
No. What I'm saying is, let's go so here, the KKT conditions, I mean, you have to be very careful about how you state it to say it's necessary and sufficient. So I'll state one carefully. Ready? It says this. If a problem is convex, in fact, I'll just say the true statements. Ready? So the true statements are as follows. If a problem, no assumption on convexity, if a problem has strong duality obtains for it, then the primal and dual optimal points will satisfy KKT conditions, period. By the way, this is very much like saying when you minimize a non-convex differentiable function, at the minimum, the gradient will vanish. That's true. The converse is false, of course. Same here. Okay, so that's the analog of that classical calculus statement. Then the next one says this. If the problem is convex and a set of points satisfy the KKT conditions, then in fact they are primal and dual optimal. Okay. So at that point, if you wanted to, you could say something like this. For a convex problem, primal dual optimality is if and only if KKT holds. So that's one way to say it. Now, if you want to have a one-sided statement to say what's the condition, I mean, if you think about it, all of the duality stuff we've constructed is sort of, we've constructed it. I mean, after a while, it will become quite natural, but it's sort of like the Fourier transform. It's not, it's a cognitive construct. We made it up. So after you start thinking in the Fourier transform, then someone is allowed to give you an answer that involves the Fourier transform. Once you start thinking about duality, which you will, I promise, in the next couple of weeks or whatever, then it'll be natural for me to just say the statement I said. However, if you just say, look, I don't care about, what's this duality? I don't even want to hear about it. I have my optimization problem, and I want to know when is x optimal. Okay, so if you want a one-sided statement that only focuses on x, then it has to be this one. It would be something like this. X is optimal if and only if there exists lambda nu that satisfy KKT conditions. That is almost necessary and sufficient conditions for a convex problem. It's not quite, because you have the possibility that, for example, Slater's condition doesn't hold and you have positive duality gap and all that.
Where does convexity enter into what you just said?
Into what I just said?
Yes.
When you remove the convexity assumption, all statements go away. Oh, except the necessary ones, right? So it's exactly like sort of going back to calculus or whatever and gradient vanishing. So it's got the same status, works the same way, everything like that. So.
But I mean, how did you get the fourth condition?
Where did I get what?
Where did you get this statement from?
Which one?
It's in parentheses, the one that says and convexity.
Here?
Yes.
Oh yeah, I'm just saying, look, the fourth condition is this. Provided it's a convex problem, means f0 is convex, fi is convex, hi is affine. Also, lambda I are positive. Therefore, this function here is convex. Gradient of a convex function vanishes, differentiable, done. It's minimized. So that's the logic there. Yeah. No, so, I mean, there's a lot of, it's not totally straightforward, all the logic here. I believe I have now confused everyone. I don't see anyone who's not confused. So that's a good time to move on. Okay. So there are some examples of this. Let's do a quick example of an application of this. It's water filling. This comes from communications and information theory. But actually, there's problems like this all over the place. In fact, well, doesn't matter. But we'll just look at it as a canonical example. And let me just explain what it is. You're maximizing the sum of the log of xi plus alpha I. And I can even sort of, I won't do a good enough job to explain to people who don't know about this. But for those who do, I'll connect it. Log of xi plus alpha I. Here you're doing something like you're allocating power to a bunch of transmitters. By the way, if you don't care about communications, ignore what I'm about to say. You're allocating a total amount of power, say 1 watt, to a handful of transmitters or across different channels or something like that in the communication system. Log of a constant plus a signal-to-noise ratio is actually going to be is proportional to your actual bit rate obtained on that channel. So this says maximize the total bit rate by allocating some power across some channels. Okay? By the way, this is used, for example, now in DSL. It's used actually everywhere. Okay? So, and I'm not talking about used by professors. I'm talking about like it's used when you use DSL, for example. So, okay. So otherwise, for everyone else, it's just maximize the sum of the logs of xi plus alpha I, subject to this. And you can even get some intuition about how this is going to work. Here, obviously log is concave, so you have sort of diminishing returns. That if you look at how much power you put in, or how much xi you allocate here, if alpha I is small, then putting some xi into that channel is going to give you a very nice rate. Once alpha I is big, the incremental return is going to be very small, right? So it's kind of clear that you want to allocate x, because we're allocating a total of 1 here. You want to allocate a bunch of the x's to the small alpha i's. I mean, that's clear. Exactly how to do this is not clear, but we'll see how that works. Well, if you write down the KKT condition, it's very, very simple. It's this. It's that x, of course, has to be primal feasible. That means it's a probability distribution. It adds up to 1 and it's non-negative. We have a Lagrange multiplier lambda associated with this, these inequalities. And we have a Lagrange multiplier nu associated with this equality constraint. And you just write out what it is. I mean, you write this thing plus actually minus lambda transpose x. That's the term, because this term, when you want to put it into a Lagrangian, becomes minus to flip it around to make it negative. It's minus x is less than or equal to 0. So this is minus lambda transpose x plus nu times, nu is a scalar, times 1 transpose x minus 1. Okay? Now, you differentiate that with respect to x. It's separable in x, right? The terms, it's completely separable in x. So partial L partial xi is 0 is this. It's nothing but that. Okay? Then you have the complementary slackness. It says lambda I is 0 if xi is positive. Okay? Soon, by the way, we'll get later this lecture to what lambda I is. It'll have a beautiful interpretation, as in communications as well. It'll work out beautifully here as to what lambda I is. Okay. Now, this is the KKT conditions. They have to work here. By the way, the stronger form of KKT conditions says this. Linear inequalities sort of get a free pass in the strong form of KKT conditions. So weak form of KKT conditions says there must be a point that satisfies the inequalities strictly. Now, of course there is here. Obviously there is. You just take x equals 1 over n, xi equals 1 over n. So the strong form of KKT holds here. But you don't even need that, because if the inequalities are linear, they sort of get a free pass in Slater. Okay? They go back to just mere feasibility. So, okay. So, but Slater holds, so everything's going to work. Strong duality obtains everything. Okay, so the conditions are this. Lambda is bigger than or equal to 0, complementary slackness, and this is this gradient condition. But let's take a look at this. That's non-negative. Okay? So let's actually try to figure out what happens. If this is non-negative, it says nu for sure is bigger than 1 over xi plus alpha I, period. Okay? Now, 1 over xi, nu is less than or equal to, because you add a non-negative thing to get nu. So nu is less than or equal to 1 over xi plus alpha I, but 1 over xi plus alpha I, if xi goes between 0 and 1, it varies between 1 over alpha and 1 over alpha plus 1. So in particular, if nu I were less, if nu is less than 1 over alpha I, then here you absolutely have to, you must have lambda I equals 0, period. And then in fact you get xi. Xi is 1 over nu minus alpha I, just by solving these equations. I'm just arguing from the KKT conditions. Okay? Now if nu is bigger than 1 over alpha I, then lambda I has to be equal to this, period, and you have to have xi as 0. Actually, the argument really goes like this. If nu is bigger than 1 over alpha I, you have to have xi equals 0, and therefore lambda I is this. So, okay, but now you have an explicit formula for x as a function of nu. Nu is a single scalar variable, and you basically have this. You have the primal feasibility says 1 transpose x is sum of this, because you get a formula from this for what xi is. It's just max of 0 and 1 over nu minus alpha I. That sums up to 1. This function here is monotone increasing in nu, and therefore there's a point where this is equal to 1. So, by the way, this is sort of a classic example. This is what you'd find kind of in a, to me, this is kind of old-style calculus or something like that. But I give it as an example. Let me tell you why I call it old-style calculus. Yeah, it's one of this, what is calculus? Calculus goes like this. You say, look, here's what a derivative is. Here's what a Lagrange multiplier is. Here are these optima. You write down all these conditions. It's like differential equations or something, and it works like this. Then in that class, they show you 12 of the 17 total cases known to mankind where you can actually solve those equations. And you know what I'm talking about here? Right? So you have a differential equation, and you look at 12 of the 17 that you can actually solve. No one who actually does anything solves things analytically. No one has done that since maybe the 1940s or something like that. I mean, it's some fantasy from the 18th century or something like that that persists. Okay? So a lot of people, they show this as an example. They say, look, isn't this nice? So you can do it analytically. Actually, this is all quite silly. Because, for example, I just add one little minor variation on this. And in fact, you can't do it analytically anymore. But the computational complexity of solving it is the same. So I just mentioned this is kind of a classical one where you can actually write down the KK conditions and solve it. That's really not the point of the KKT conditions. I just want to emphasize that. We'll see later in the class how people would say, it's actually even funnier than you think, because people would say things like, no, defending a so-called analytical solution, they'll say things like, oh, no, but an analytical solution is much faster. Actually, that's false, in fact. It's just completely false. Actually, computational complexity, if you solve this problem by methods later in the class, will be faster than, in fact, doing it by this so-called analytic solution. Yeah?
Do you need to solve the problem for every single alpha I? It seems like...
Alpha I are problem data. They're just problem data. So, in fact, they are the only problem data here. So, to solve this problem means to be given a set of alpha i's, do some thinking, and to return the optimal allocation xi. So, in that sense, yes, you do. So,
I just asked because nu is compared to 1 over alpha I, but
yeah.
Nu is just a single number, and alpha I seems like it would vary a lot.
It does.
So which one do you compare it to?
Well, in each of these, you're comparing it to one of them, and then you add those up. So that's how that works. Here's the interpretation, which gives it the name water filling, is this. So there's a way to interpret this very nicely. What you do is you make heights alpha I, like this. And then you pour in some water here. And so you flood this area with, say, a unit of water. Or actually, in general, you flood it in the communication context with this right-hand side is P, which is a total power that you're going to allocate to some channels. You flood it, and the height, the depth of the water gives you the optimal x. Okay, so that's the picture here. And it's actually kind of nice. It says that basically if alpha is high enough, if you become an island, and you allocate no power. And so if you do communications, it makes perfect sense. It says if the signal-to-noise ratio is really bad, here's the amount of power you allocate to that subband or whatever, 0. Because it just doesn't make any sense. Okay? If alpha is really small, you're going to allocate power to it. And the amount you allocate goes something like this. Okay, so that's an example. One of the, by the way, very small handfuls of examples where the KKT conditions actually leads to a solution of a problem, right? So, okay. Now we're going to look at actually a very useful interpretation of Lagrange multipliers. And in fact, it is what makes Lagrange multipliers extremely useful in practice. And this part is generally not emphasized. Certainly people know it. It's actually shocking how useful this is in a lot of practical contests. So here's what it is. Let's take our original problem. That's this thing here. And what we're going to do is the following. We're going to perturb, notice the period. Everything's cool here. Right? See that min means it stands for minimize. That's what the period means. Okay, so S2, that's subject to. So everything's cool here. So what you do is you perturb the problem. Now, by the way, this is sort of a multi-objective. It's sort of like a multi-objective, multi-criterion problem or something like that. But you talk about, in fact, perturbation analysis of a problem is to look at the solution of this problem as a function of UI and VI. Actually, that's extremely useful and actually generally should always be done. No exceptions. In fact, we'll see it's, generally speaking, it's locally done for you when you solve the problem, whether you like it or not. We'll get to that in a minute. But so let's actually just stop and say what this perturbed problem means. If ui is 0 and vi is 0, this thing is the same as that. Now, if I increase u1, if I make u1 equal to 0.1, for example, then the way you'd say that is you'd say you have relaxed the first constraint. Because, well, you increase the feasible set. So you've relaxed it. Okay? And it has lots of interpretations. F1 less than or equal to 0 might have been a limit on power in a circuit, for example. When you relax it to Fi is less than 0.1, it might have said that you just threw another 100 milliwatts at a circuit. Okay? So that's sort of the idea here. It could be a constraint on anything. Okay? And you just relaxed it. All right. Now, if ui is minus 0.1, you've restricted, you've tightened the first constraint. So you should think of ui's as loosening and tightening knobs for the problem. Now, of course, if you tighten, if this thing is feasible and you tighten this, it could be infeasible, in which case p star goes to plus infinity, the optimal value. Okay? You can't interpret the VIs as loosening and tightening. Actually, what they are is you're shifting. So you're really saying, you know, for example, an equality constraint might be in an optimal control problem that you hit a certain target. If you mess with the VIs, you're just changing the target point. Okay? Is it loosening or tightening? Doesn't make any sense. You're actually shifting the affine constraints in the feasible set. So it doesn't correspond to tightening or loosening, either one. Okay. Now, what we do is you look at p star of uv. That is the optimal value of this problem as a function of ui and vi. By the way, that's a convex function in u and v. You know that. Okay. And it's really interesting. By the way, it's very interesting thing to say what this is a very interesting thing to look at. And I should mention a few things. If you were to just take one u1, say u1, and plot u1 versus p star, you'd get some convex curve. And that of course, would be the optimal trade-off of f1 versus f0. That's exactly what it is. Okay. Now, so p star, this gives you the optimal value. And you shouldn't confuse what it is. It really means the following. It means, for example, if I were to allocate you another 50 milliwatts of power for your circuit, and this is the important part, and you were to re-optimize the entire circuit to use that extra power, then this is how much better you would do. Okay? That's very different from a different type of, another sensitivity says, what happens if you wiggle this but you don't re-optimize? That's a different kind of sensitivity. This is sensitivity in design. So you're given something, or if someone takes something away from you by tightening a constraint, you completely re-optimize, and then you evaluate what's happened. And because, in fact, someone could take a lot of a resource away from you, and you could design around it. And, which is to say, you could re-optimize everything else, even though they've taken a huge amount of resource away from you, you're not doing much worse. Everybody see what I'm saying? Okay, so, and we're going to see all of that and how it all works. Okay, so this is the perturbed problem. Now, the dual of this is in fact just that. You can just work it out. So here it's maximized g of lambda nu. Here it's maximized g of lambda nu minus u trans. Actually, it's extremely simple to show. Minus u transpose lambda minus because this what was a 0 here becomes a u. I mean, it's very simple here. You get this. Okay. Now, what we're interested in is what can you say about p star of uv? What can you from the unperturbed problem and a dual optimal solution? And so you get these global sensitivity results. You're going to do something on this on your current homework. Some of you may already have, but maybe not. You all will have, I think. I actually can't remember. Is it this homework? Okay. We're deeply pipelined. We're working on your homework 2 weeks from now. So the one homework you're working on is in our distant and hazy memory. So, okay. So you have the following. Assume you have strong duality for the unperturbed problem, right? And lambda star and nu star are dual optimal for the unperturbed problem. Then you have the following. P star of u and v is bigger than g of lambda star nu star minus this. So you get these, just this affine thing. Okay? And let me just quickly draw a picture just to show you how that looks. Here might be u, as you change u, and here's p star of u. And it basically says that there's an affine function here that lies below p star of u. I mean, it kind of makes sense. But anyway, this is it. Now, this condition is really, really interesting. So this star, the p star of 0, 0, that's the optimal value of the unperturbed problem. And so it says the following. It says if you tighten or loosen a constraint or change an equality constraint in a problem, it says, and actually this doesn't require convexity here, but doesn't matter. We're going to be interested in this in the case when it's convex. Then it says that this optimal value as a function of u and v. U are the tightening parameters, v are the shifting parameters. It says it's the change, if I were to subtract that over there, it's pessimistic. Note that this is an inequality constraint. So it says, what it guarantees you is you will do worse than the following. Worse means you'll be at least this value in optimal value. You will be at least as bad as minus some ui lambda I star minus some vi nu I star, period. It says you will do at least that bad. You might do much worse, including possibly the thing will become infeasible and this becomes plus infinity. Okay? That's infinitely bad. And now this means because this is a global result, this doesn't hold for u and v small. This holds for all u and v. Okay? So, okay. Now, because it's this global thing and it's an inequality, basically it's a pessimistic result, it actually is asymmetric. It makes weird asymmetric predictions about what will happen. It says basically there's cases where it says the following. Here, let's look at this. Let's look at a large Lagrange multiplier. If you have a large Lagrange multiplier, then it says if you tighten that constraint, you are absolutely guaranteed that p star has to go up. Period. It may go up even more. It may go up to plus infinity. That's as high as it can go. Okay? Meaning you've tightened that constraint and it's become infeasible. But it guarantees sort of a minimum amount that the performance deteriorates. Okay? What's interestingly, if you then take lambda I, if lambda I star is large and you loosen it, you might think, oh great, then my objective will go way down. And that's actually false. It makes no statement. It might not even go down at all. Okay? Because this is an inequality. And so you can work out various things here. That's what these are. You just have to look at them and see if you believe them. Now, this is a global result. You can also look at this locally. And you can, let's consider the case where this optimal value of the problem as a function of the perturbation parameters is differentiable. In that case, you have unbelievably simple formulas, and here they are. And this is it. I mean, that's the formula. That's what you want to think about. That's right there. So, lambda I star is the partial derivative of the optimal value with respect to ui. Period, with a minus sign. Okay? If it's differentiable, by the way, it is often the case that p star of uv is not differentiable. In which case, the right-hand sides here have no meaning. Okay? I mean, the global result always holds. Always. This local one requires differentiability. But in terms of interpreting it, it's just beautiful. And let's actually just talk about what it means. Actually, let's look at complementary slackness. Ready? Let's do this. Let's solve an optimization problem. And let's suppose that f3 of x star is equal to minus 0.1. Okay? What does it mean? It means that the third inequality constraint is slack. It's not tight. Okay? Now, let me ask you this. Suppose I go back to my original problem, which is this, and suppose I perturb the 0. In fact, let me tighten it. Well, let me loosen it. Let's loosen it to plus 0.01. How does p star change? Not at all, because the same x star is optimal. So p star doesn't change at all. I can tighten it. By the way, I can tighten it by, for example, 0.01. I can replace 0 with minus 0.01. If I replace 0 with minus 0.2, what can you say? Actually, we can say very little, other than it will get worse or stay the same. Okay? So it could actually stay the same, and everything in between is possible. Okay? What is lambda 3 star? Lambda 3 star, it's 0. It has to be 0. And you can, well, first of all, you could just say, look, complementary slackness. Look, minus 0.1 times lambda 3 star has to be 0. That's complementary slackness. Obviously, lambda 3 star is 0. Okay? But in fact, you get it from the sensitivity. Lambda 3 star equals 0 means you can wiggle the right-hand side of that constraint, and it will have no effect whatsoever on the optimal value. Everybody understand that? And it's completely clear. Okay? So this makes, so now you know what it means if you have a big Lagrange multiplier, optimal Lagrange multiplier, or small. Big means that constraint, first of all, it better be tight. Has to be tight. Okay? It's tight, and it says that constraint is, well, let's see. So far we've had a qualitative idea of tightness of a constraint. You simply solve the problem, and you look at a constraint, if an inequality constraint. If it's equal to 0, we say it's tight. If it's less than 0, we say it's slack or not tight. Okay? You now have a numerical, a quantitative measure of how tight it is. Right? This is fantastically useful. Let me explain sort of in practice how this works. You know, if you start doing this, what will happen is you'll have a whole bunch of constraints, and you'll solve a problem. And we'll look at, you'll look at f1 of x star, you'll look at f2 of x star, and so on, and you'll look at f10 of x star. Okay? And these might be, let's put down some things these might be. Well, let's suppose that all of these are actually 0. Okay? What does it mean? This means that when, at least for the solution you found, x star, all of these constraints are tight. You know, that's your constraint on power, that's area, you know, I don't know what this is some timing. They're all tight. Okay? Now, by itself, this is like, so what? I mean, doesn't tell you that much. If I write down an optimal Lagrange multiplier, things are going to get a lot clearer. So suppose I write this, right? And this is 10. It just doesn't matter. Let's make this 3. There you go. Right? And this one is 0.02. Now, what does this mean? We know that the first constraint, second, and third are tight. Okay? And if you saw these numbers, and I don't want a precise mathematical statement. I want just what would this mean in the context of solving that problem. It has a very strong meaning. What does it mean? And I want just a rough statement. What would you say about this?
The sensitivity of optimal value with respect to the constraint.
Right. It says that you would say something like this. Someone would say, well, are all the constraints tight? You'd say, yep. But the second one, this sounds weird, is much tighter than the other two. I know that sounds weird. It's a violation of, you know. It's be like saying, is that matrix singular? Right? And if you're in certain contexts, you're allowed to say things like almost, or nearly, or effectively. Okay? And that means you're talking about singular values or a small or a very large condition number. And it makes a lot of sense. You can say the same thing here. Okay? And what you would see here is that, for example, F2 is the constraint. If someone were going to give you some more resources and you wanted to ask for more resources, you'd actually ask for F2. Whatever F2 represents, that's the resource you'd ask for. If someone said, we're tightening budgets, take something away, then you'd say, okay, please let's make it resource 1, for example. By the way, it doesn't guarantee anything, okay? Nothing is guaranteed. What this says is that this right-hand side 0 in the inequality can be wiggled a little bit. And at least locally, I can wiggle a little bit and have essentially no change in the optimal value. By the way, that does not mean x star. You have to do a complete redesign. So in fact, the correct interpretation is you could wiggle U1 a little bit, and a redesign will work around it. The concept of the redesign is actually extremely important because that's what this kind of sensitivity is. So basically, someone takes away a little power from you, and you're like, okay, no problem. And you redesign the whole thing to basically achieve all the other specifications. It's very little worse, but it now takes up less power or something like that. So that's the idea. And so this is just, I mean, this has huge implications. in practice, and in a lot of cases it's just not, either, well, it's a disconnect, right? Anyone who knows anything about optimization knows about these. And almost universally, people who do optimization in application contexts don't know what about these. So it's like a perfect disconnect here. Okay, so, but now you have this is the correct interpretation of Lagrange multipliers. Okay? And in fact, if you go back, you get beautiful, beautiful interpretations. For example, here in water filling, the lambda I now have a beautiful meaning. Lambda I is great. It's basically, look, you're violating this constraint. That's the same, by the way, of sort of reducing alpha I. So it basically says, you know, if I were allowed here to sort of reduce that's something like a noise level or something like that. If I were to reduce my noise level, how much more net total bandwidth would I get for the same power? And that's exactly what lambda I is. It gives you the partial derivative of that. All right, so it's literally in, you know, bits per second per watt is the unit of lambda I here. Okay. All right, so this this finishes this. By the way, there's other interpretations of duality. They're in the book. You should actually read these. I mean, just read them because they're just supposed to give you a feeling for what it is. It's very important you have a good, I mean, in addition to knowing all the math, have a good feeling for what these mean. They generally have interpretations of things like prices. And these examples are given. There's also examples in mechanics and other things, and you can look at these. We'll see lots and lots of examples of these. It'll come up in all sorts of contexts.
When you were saying earlier about cutting resources with,
yep.
From lambda 2 or from F2, did you mean just decrease the right-hand side of
That's exactly what I mean, yeah.
So you go negative?
Yep, you go negative. That's tightening that constraint.
Okay.
And here, you're guaranteed. I can tell you that if you tighten U2 for this problem, I can give you a lower bound on how bad things can get. You can tighten U2, and P star can go to infinity, which is to say it's not feasible. So I can't give an upper bound if I tighten U2. I can give you a lower bound, though. If I tighten U2 to minus 0.1, for example, then someone tell me here how much P star is going to go up by at least.
1.
1, precisely. So it'll go up by 1. Could go up by plus infinity. If you tighten U2 to minus 0.1 and the problem becomes infeasible, then it went up by plus infinity. But it has to go up by 1, period. So that's the picture. Okay. Now, let me also put this in perspective. It's going to turn out the following. For the things we're going to look at this quarter, not next quarter, but for this quarter, although duality plays a central role next quarter. But when you look at, sorry, I know you're not thinking about next quarter. As a zeroth order statement, the following is true. When you solve a convex problem, you're going to get the optimal Lagrange multipliers whether you like it or not. It's just, in fact, we'll see all this in a few weeks. I mean, that's basically how they're solved. I mean, and you've heard things like primal dual solvers, or you may have heard of this or whatever, but it doesn't matter. Even if it's not a primal dual solver, whether you like it or not, you will not be given just X star. You'll be given X star, lambda star, nu star. And that's universal. So any solver is going to do this, period. You may not care about lambda star, nu star. You may only care about X star. Fine. But the point is, they're there. Maybe they're not being returned to you. Maybe they're being returned to you and you're ignoring them. They're there. What that means is, basically, these optimal sensitivities, if you want to call them optimal sensitivities, they're free. They're free. You design a circuit, period. You get these optimal sensitivities. You can ignore them. Fine, no problem. But the point is, they're absolutely free. They're just there. You solve a maximum likelihood problem, these things are there. You do experiment design, these things are there. You do finance, they're there. So actually, that's why actually all the duality we're talking about actually has huge applications, because this all comes for free. These are not, there's no additional cost to calculating these. You get these whether you like it or not. So seems to me the right policy is when something comes to you for free, you should figure out some way to use it. And they're just fantastically useful just to look at. So this is a matter of course. And if you look at any solver, and I mean like a low-level solver, one that solves an LP, a QP, an SOCP, an SDP, maximum entropy, any of these, absolutely no exceptions. it will return dual feasible points. I mean, that's just part of the deal. Actually, if for no other reason than to certify the solution, right? Because that's what's considered in convex optimization, what it means to solve a problem. You don't just say, here's the answer, I think. You say, here's the answer. Oh, and there's no reason you should believe me, so I'm also providing optimal Lagrange multipliers, which in fact form this certificate proving that what I have alleged is the answer is in fact the answer. Everybody see what I'm saying? So that's just sort of the social contract you have when you have a solver for convex optimization. That's what you get, right? So then there's no questioning. I mean, there's no, then, by the way, it's none of your business how they solve the problem, because they've returned not only a solution, but a proof, a certificate proving it's the solution. And then it's none of your business. They could have figured it out X star by using a stick or something like that. But, I mean, look, it's fine. Doesn't matter. If the certificate checks out, that's the end of that. That's the end of the discussion. Okay?
How do you physically check with the certificate in your hand?
You evaluate G. So you evaluate G, and I mean, first of all, if you want to do this in a way where you don't trust the solver, it's extremely simple. Somebody gives you x, let's call it x tilde. We'll take the tilde off and put a star on it only after we certify it. So they return to us x tilde, lambda tilde, nu tilde. Okay? Tilde because it hasn't been verified yet. Right? So we're doing safe optimization or something like that, right? So the first thing I do is I take x tilde and I check if it's feasible. If it's not feasible, I leave a bad review for that solver. I go back and leave some customer feedback and say, come on, they returned to me a point that was they alleged to be optimal. It wasn't even feasible. Okay? So if x tilde is feasible, I then check that lambda tilde is bigger than or equal to 0. Okay? If they have a negative lambda tilde, I give an even sillier, I give an even worse review of that solver in a reputation system. Okay? If lambda tilde is bigger than or equal to 0, now I go back and I check the KKT condition with the gradients and whatever, the fourth KKT condition. If that gradient is not 0, then I say, come on, please, stop messing with me. Okay? If it's 0, then I know what G of lambda star nu star is. G of lambda tilde nu tilde is. If that number is equal or very close to F0 of x tilde, if it's within my threshold, it's certified. End of story. That's it. And I go and I leave positive feedback for that solver. Okay? So that's how you do it. Okay. All right. Next topic is really interesting. And let me explain what it is. Is a question.
So for non-differentiable, do you just skip the checking the differentiability step and go straight to the evaluating G?
There is a direct variation, extension of KKT conditions for non-differentiable. And he uses the idea of a subgradient, not a gradient. So there is an extension of it, but we won't do it in this quarter. In fact, generally this quarter, the way things are going to work is this: you can actually reformulate your way. It's a good topic. It's related to the next topic. You can reformulate your way around almost all non-differentiable problems, right? In fact, it's shocking the extent to which you can. I mean, let's look at an example, right? So suppose someone says, well, I want to minimize, note the period, ax minus b infinity, like that. It's horribly non-differentiable. I mean, the objective here is piecewise linear. And whenever one entry of ax minus b hits the maximum and takes over to the maximum, you got like kinks in the objective. This is horribly non-differentiable. Okay? So you say, well, that's it. KKT, I can't do it. But interestingly, we know how to how to reformulate that. That was all the stuff we did in the last week or two. What you do is you rewrite this as, I mean, there's lots of ways, but this one you might write as t. That's a new variable, subject to ax minus b is less than t1, and it's less than minus t1, like that. Okay? Now, what's super cool about this problem is it now has n plus 1 variables. It also has 2m linear inequalities. But notice now, totally differentiable. So I cannot apply KKT to this, because F0 is non-differentiable. I can apply KKT to this. So you see what I'm saying? Yeah. So for us, mostly for non-differentiability, our policy generally, pretty much for this course anyway, is to reformulate our way around it. So, however, having said that, there is a generalization of KKT to directly to non-differentiable cases. So, okay. Now, we're going to do something that's actually very interesting here. And let me give you the big picture first. So here's the big picture. And at first it seems ridiculous. So let me just show you what it is. So suppose I have a problem that's P, okay? And we know how to form a Lagrange dual. We'll call that D. Okay, so we have a fixed procedure by which we can do this. Okay, so that's, and you know how to do it. I mean, you take the original problem, you form a Lagrangian, minimize over X, maximize that, call that G, maximize G subject to lambda, you know, that's it. That's this thing. Okay. All right, now what we're going to do is this. I mean, this is just really dumb. Here's what we're going to do. We're going to take a problem, and we're going to do an incredibly stupid equivalence with it. And I'm going to create something called P tilde. I mean really dumb. Wait till you see how dumb these reform. They're nothing. This is a sophisticated reformulation. Okay, we're not going to do that. We're going to do like, you'll see how stupid these reformulations are. I mean, we're talking really simple here. Okay, like introducing a new variable and saying it's equal to the old one. I mean, literally things like that. I mean, that's how dumb it is. Okay, so we're going to do that. Well, so this is completely trivial. And then, of course, well, we know we can form a Lagrange dual like this. Okay? Now, aesthetics would suggest that these two problems should be trivially related. That's what it would suggest, right? And in a sense, they are. Because, for example, D and D tilde are related because they are the duals of primal problems that are trivially obtained one from the other. Okay, and so you want to add this in. I guess when you do this in math, it's called a commutative diagram because it means you kind of either way you go, you kind of get the same thing. You want to do this. Well, guess what? This doesn't work at all. These can be. They can look wildly different. I don't want to say they are unrelated. They are related. They're related this way, only this way. But there's no obvious connection between the two, and we'll see stunning cases where the most mind-numbingly stupid transformations of a problem, if instead of forming a Lagrange dual, you first transform it in a profoundly stupid and simple way, and then form a Lagrange dual, you get something totally different. I mean, totally different. We'll see examples soon. Everybody see the picture? Now, at first, this looks bad because, well, first of all, it's unaesthetic. You wanted a beautiful picture with, well, if you're trained in math, you want to draw that last thing. That's called a commutative diagram. And anyway, you'd want it to work that way. At first, it's upsetting that it's not there. Actually, it's very, very good. Because it's going to be interesting because it means that, so there's the idea of weak, not weak, but there's sort of you can do the basic Lagrange dual, and that's where you just follow the book. Somebody gives you a problem, you form the Lagrangian, you form a dual function, maximize dual function subject to lambda positive. That's like by the book. Okay? This fact that there's not a commutative diagram here says there's actually some art and I mean there's all sorts of interesting things. It means that if you're willing to call this this one you would really call the dual because it's created by just turning the crank. No creativity. This one, I guess probably the technical term is it's a dual of that problem. Okay? So generally when people say, derive a dual or something like that, it's actually quite interesting now because it allows you to do some transformation. I'm talking about how this is interpreted on the street. Okay? So if you're in a courtroom and someone says, find the Lagrange dual, you do it by the book. Okay? But if you're among friends and things like that and someone says find a Lagrange dual, you can actually transform it slightly, then form a Lagrange dual, and then someone would say, is that the dual? You'd say, well, no, it's a dual. And in fact, if you look in the literature, that's why you'll often see these duals with different names. So if you read a lot of the literature, which I don't really recommend, but if you were to do that, you would find things like, the Frank Wolf dual or the Smith dual, or I mean, they have all sorts of names, and they just follow this thing. Okay, so, all right. So I've made these points here that equivalent formulation problem can lead to very different duals, and let's look at some examples of it. I mean, so here's the most, here's a dramatic example. Okay, it goes like this. Ready? An unconstrained problem. Actually, you know, we haven't had a discussion of the dual of an unconstrained problem. So let's have it now. It's going to be a very short discussion, by the way. So there are no constraints. So what's the Lagrangian? Well, for each constraint, we should add a term, lambda I fi, to this objective. And for each equality constraint, we should add nu I hi. But there are no constraints. So you're looking at the Lagrangian. That's the Lagrangian. And there are no dual variables. Well, there's no constraints. All right, fine. You turn the crank. The next step is to calculate g, the dual function. How do you calculate? Well, you minimize the Lagrangian. So you minimize this. The minimum of that is p star. Right? I mean, period. Therefore, there's a dual function. You know, it's a bit, I mean, I don't know, you could argue about semantics here because it's a strange function in the sense that it actually has no arguments. But imagining you could pass something to g, which you can't, it would return the answer p star. Okay? So now let me tell you the good news. Good news is we have a zero duality gap. By the way, p star is an excellent bound on p star, lower bound. As lower bounds go, they don't come better. But it's completely useless. It's a tautology. It's utterly useless. All right. Now watch this. I mean, look at this problem and this problem. I mean, you can't get a stupider transformation than that. This basically says, I'm going to introduce a new variable. I'm going to call it ax plus b. That's all. I'm going to call, sorry, it is ax plus b. I'm going to call it y. And so I'm going to minimize f0 of y subject to y equals ax plus b. That's what this is. Now, you have to admit, as transformations go, I mean, and by the way, this is so stupid that anybody who starts this way, you should think, look, this is so dumb and simple. There's no good. Nothing interesting is going to come of renaming something. I mean, that's all this is. It's just renaming something. Technically, it's not. You've actually introduced a new variable and new equality constraints. Okay? But the point is, this is no deep, this is not a complicated transformation. Okay. Now, the dual here, however, is this. You form the Lagrangian. It's f0 plus nu transpose times ax plus b minus y. Okay, this is the Lagrangian. And you minimize that, and you get something interesting. You get minus f0 star plus b transpose nu if a transpose nu is 0. And so the dual is this. So here, the original problem, unconstrained problem, had a completely useless dual. The dual function was just p star, just a constant. Now you get something that's not remotely obvious. It's this. It's different. And let's just look at an example. I mean, here's an example. Minimize norm ax minus b. Oh, we do that all the time. This is a general norm, by the way. This is not 2 norm. Okay, so just general norm. Minimize norm ax minus b. Well, if you just form the Lagrange dual, if you're on the stand under oath and you're asked to form the Lagrange dual, you say, yes, I've done it. They say, can you tell us what the dual function is? You say, no problem. It's p star. They say, what's p star? And you go, it's the minimum value of ax minus b norm. And then there's nothing that's it. That's all you say. You just say that. You'd say, that's a lower bound on the optimal value of this problem, which is also p star. So everything's cool. If you apply this procedure, you end up with this. I mean, you minimize norm y subject to y equals ax minus b. Well, I mean, come on. Transformations don't get simpler than this. You derive the dual of this, you get something very interesting. You end up with the following. You work out what the conjugate function of the norm is, and the conjugate function of the norm is the indicator function of the dual norm unit ball. I think we've actually done that. But what happens is you end up with the following problem. The dual of this. Now, by the way, this is sort of a Lagrange dual. So you can say the Lagrange dual of this and this. This is the Lagrange dual of that. Is this. You maximize b transpose nu, subject a transpose nu equals 0, and nu in the dual norm is less than 1 in dual norm. Sorry. Okay? So this one is useful. It has huge number of uses, actually, tons and tons of uses. It is not obvious at all. Now, by the way this would work is this. Some people would, so there's many ways you could say this. You could certainly say this is a dual of that problem. And someone says, really? And you'd say, okay, look, technically, here's what it is. It is the Lagrange dual of a trivial reformulation of this problem. That would be if they ask you really how you do it. Because there's actually other ones, and you'd get other duals, even for the norm approximation problem. And that's why if you look in the literature, you'll see all sorts of different duals. And you'd see the Smith dual and the Frank-Wolf dual and the dual and blah, 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 like that. Okay? That's why it is, you could say, you could look up QP duality and find 4 different duals. Okay? One will be the dual that just turns the crank that we have. Others will be ones where there's some slight reformulation, and then you form a Lagrange dual. And they'll look different. They'll look as different as these. So, anyway, yeah?
What happens to the duality gap if you create multiple duals?
Nothing. Nothing at all. So, here, in fact, let's talk about duality gap. For this problem specifically, somebody tell me, what is the optimal duality gap for this problem? 0. Why? It's absolutely 0. So, in other words, there is no issue. This problem and this problem, same optimal value. Why?
Convex and Slater holds?
Yeah, so Slater holds trivially. Slater says any inequality constraints, for any inequality constraint, for the inequality constraints, there must be a point that satisfies them strictly. Well, look at that problem. There are no inequality constraints. Therefore, Slater holds. There's nothing to show. Done. So P star equals D star. Now, since these two obviously have the same optimal value, therefore the optimal value of this one and this one hold. So it works. Okay. So there's another trick, which is this. And we've already seen this a couple of times. You can actually... There's a difference, explicit and implicit constraints. It doesn't really matter generally. I mean, it's kind of just a trick in labeling, in general. When you form a dual, it is not a trick. So you will get different duals. So if you include, when you have a constraint, you can either explicitly declare it in your list of constraints, or you can sort of secretly attach it to the function, the objective object, as part of the domain. Right? Everybody, so... And I mean, if you look at these originally, these are just sort of reformulations, and it's just kind of trickery. But you can imagine sort of, if you imagine, say, software that implements, you can imagine how this might work. They'd actually be a little bit different. In one case, it's in the domain of the objective. For that matter, you could sneak it into the domain of one of the constraint function or whatever. Or you can just have a domain of the problem, but that doesn't matter. So let's see how that works. So here's a problem which says minimize a linear function subject to equality constraints and a box constraint on x. Okay? That's obviously an LP here. You can write it out as an LP. This is an LP. That's the dual LP. And you have Lagrange multipliers for the two inequalities. That lambda 1 is for this one, lambda 2 is for this one. Oh, say, this is fun. Let me just mention something since we just covered this. It's actually quite interesting. What can you say about the entries of lambda 1, very poor choice. Sometimes you'd call this lambda minus and that lambda plus or something, because it's the upper and lower bound. Can the entries of lambda, could the third entry of lambda 1 and lambda 2 both be positive? And if the answer is no, explain to me why. Complementary slackness, fine. So, but finish the argument. I agree. Finish the argument.
Then x3 is plus 1 and minus 1.
Yeah, so if the third component of lambda 2 were positive, by complementary slackness, x3 has got to be slammed up against this inequality, and therefore x3 has to be 1, x3 star, right? If also the third component of lambda 1 is positive, then it says this inequality, x bigger than minus 1, has to be tight. And that would tell you that x3 has to be minus 1. Now, numbers cannot be minus 1 and 1 at the same time. So this is impossible. Everybody follow this? So actually, you will see this as actually a practical use for this. It means that lambda 1 and lambda 2 actually share. So actually, people will do this actually as a data storage. One trick is actually to store them in the same array. And they'll put a minus sign on lambda to code whether it's at the lower or upper bound. And so they'll actually call this lambda plus and lambda minus. It's a good trick. It actually makes sense. But you will actually see that. You go to Google and get some codes. You will find optimal Lagrange multipliers, if for what people call, you know, bound or range constraints, they will be returned as, in some cases, as one vector, where it's reported as positive if it's the upper bound that's tight, and negative if it's the lower bound. Okay. That's just an aside. It just had related to what we've just done, so I thought I'd mention it. Okay. All right, so this is the dual. Everything's fine here. Nope, no problem. That's another LP. But now what we're going to do is this. We're going to rewrite this problem this way. And then there's no, well, okay, it's clearly they're equivalent. By the way, they're not the same problem. Because actually you would get different exceptions thrown at you when you pass in x which violates the, if you give an x outside the box over here, the objective will happily be reported, evaluated. The objective functional will report its value and pass it back to you. Okay? Ax equals b. Well, let's say that's 0, and it'll come back and give you the fees token. It'll return the fees token. Then you'll throw x into the box constraints, and one or more of them will come back and say in fees. Okay? Yeah, by the way, which means that your objective value is interesting but not relevant. Okay? Now, in this problem, if I pass in to this problem an x, which is out of the box, the objective throws an exception at me. And the objective throws like an OOD token back at you, which means out of domain. Okay? So that's the difference. Of course, it makes no difference. I mean, it doesn't. But now let's form the Lagrange dual, and it'll make a big difference. Let's try it. So here, I simply take the dual function is I take f0, as usual, plus nu transpose ax minus b, this, that. And I have to minimize this over, and I've already simplified a little bit here. So really, this minus 1 less than or equal to x less than or equal to 1, to be honest with you, to be fully honest with you, this thing is actually attached to that object. It's an attribute of that object. You see what I'm saying? Because, anyway, I just pulled it out, okay? But I know how to, in fact, wait a minute. I think you solved one. Didn't you do this on some homework? This is one of your trivial LPs. Minimize C transpose X subject to X in some box. Didn't you? I think you did that. I know I talked to people in office hours about that. So, and I think they were in this class. But, maybe you did something like that, but something close to that. Anyway, the solution is very simple. You select X to be plus 1 if C is negative, and minus 1 if C is whatever. Okay. So, anyway, if you do that, then the optimal value of this thing is this. It's the 1 norm of this. And so you actually just get, sorry, it's not just C. It's A transpose nu plus C, like this. And you get that. And that's the dual problem. Okay? So here, the original problem is, and you might, by the way, to make them look more like duals, you might write this way. Yeah, there you go. So you could say, I want to solve, minimize a linear function subject to linear equality constraints and an infinity norm constraint. Then, by the way, you might say, oh, hey, here's the dual. It's unconstrained, and you minimize a linear function minus a 1 norm. By the way, when you write them out by norms, it gives people that you're getting that good duality feeling, because you know that infinity norm and 1 norm are conjugates. And so they're related by duality. So this sort of makes sense. So you would say, it depends how well you know someone and what the social context is. But it would be OK to say this is, I guess properly you'd say this is a dual of this original problem, something like that. The question?
Yeah, how did you get from the infimum of C transpose X to the next line?
You hear?
Yes.
Oh, I collected A transpose nu plus C transpose X, and I worked out this. There you go, like that. And I know what the answer to this is. I choose X to be plus 1 if the corresponding entry of A transpose nu plus C is negative. And the optimal value of this thing is the 1 norm of A transpose nu plus C. So that's what I did. It's a basic dual norm result. Yeah. Yeah, I'm not expecting you to follow every line here, obviously. I'm going way too fast. I mean, you can get most of it. So if you're getting every line, then I'm going too slow. So, and in that case, I presume I would be getting the international nonverbal signs boredom signs from you. So I should be getting that from about 10% of the class or something like that. Okay. So that finishes up. I mean, that was just a quick topic, but it's just to point out, and you'll do examples of this in homework and stuff like that. So, and you'll see it and you'll get these ideas. But the main point was this, and it's not obvious. The main point is this. Trivial reformulations of problems, you don't get a commutative diagram with Lagrange duality. So just, and it's interesting. You can get very different duals by doing things that would appear to be silly. I mean, even dumber is like if you had to take this norm problem and you minimize the norm, you could say, well, look, minimizing the norm says minimizing the norm squared, obviously, because the norm is positive, non-negative. If you then form the dual of minimizing the norm squared, you get another totally different dual. Totally different. I mean, it's not totally different. It's got the same problem data in it. It's also got a one norm in it, but it'll be different. And they'll have different uses, different applications, and things like that. So, okay. Our last topic, we're actually going to skip a very important topic. Sorry. But I'll tell you what it is. It's duality for feasibility problems. And these are actually called, but it's in the book. We do expect you to read it. And we're gonna find some homework problems on it, I guess. Or let's make sure we do. At least one or two or something like that. And in this case, you get things called theorems of the alternative. So I'm not going to cover it, because after you've sort of seen a bunch of this stuff, you can guess it. What I want to do now is, the last topic in duality is problems with generalized inequalities. So here we're going to look at, so we have a fi of x is a vector, and everything works the same, except, remember how it works in our case, is we form, lambda I fi in the scalar case, but now fi is a vector. So it's not surprising that lambda I has to be a vector too, and this becomes an inner product. Lambda I transpose fi. That's fine. Here's what's cool though. Lambda I for scalars were bigger than or equal to 0. Now, for scalars, there's not very many interesting inequalities other than the ordinary inequality. Okay, that's it. So for vectors, we have lots of notions of what it means for lambda I to be positive. And it turns out, and by the way, it had to be for aesthetic reasons, for various reasons. It had to be, lambda I has to be positive in the dual cone. Okay? And if you check carefully, it even sort of makes sense. So here's what it is. This is the Lagrangian. If you look at, so fi has to be less than or equal to 0 in the cone ki. If you look at sort of dual cones and everything, you can actually mark each thing as actually sort of being in the primal or dual space. We don't generally do that. I mean, that would be distinguished between row vectors and vectors. Or in a mathematical context, linear functionals and vectors. So we're not doing it in this abstract way, but you can do it that way, and it will work out. And lambda I transpose, that's a row vector. It's a linear functional, and it has to be the dual. It could only be the dual cone positivity. So, and everything else works. You have the lower bound property. If these lambdas are bigger in the dual cone, bigger than 0, then G is a lower bound on P star. And actually everything just, it's the same. I mean, these are 0, and then this is a product of elements in the cone. That's in the negative cone, and that's in the dual cone. And inner products of things in the dual cone and the cone are non-negative. Inner products of things in the dual cone and the non-negative negative dual cone are non-positive. And so this thing's less than or equal to 0. Everything works. Actually, everything works, including Slater and everything. And I just want to do one example of that. It's a semi-definite program. So you want to minimize C transpose X subject to, by the way, this is called an SDP in inequality form or something like that, subject to an LMI. That's a linear matrix is less than or equal to, in matrix sense, another one. And the Lagrange multiplier here is actually going to be an element of the, I have an inequality. It's going to be an element also. It's going to be a matrix inequality. So it's going to be a matrix Z, symmetric. And it's going to have to be non-negative in the dual cone. Now the dual of the positive semi-definite cone is the positive semi-definite cone. So Z is going to end up being a positive semi-definite matrix. The inner product between two symmetric matrices is trace. In general, actually, it's just trace A transpose B. But if it's symmetric, it's just trace, A, B, period. So it's the trace of this thing with a minus sign there times Z. So that's the Lagrangian right there. And you stare at it for a long time and you realize it's affine in x. We know how to minimize an affine function. It's minus infinity unless the linear part vanishes. And so you get this. It's minus infinity unless these things, that's actually the xi component of the linear thing here, unless that is equal to 0, in which case this all drops away and what's left is the trace zg. That's this guy. And so this is the dual SDP. Okay? Now, by the way, this is not remotely obvious. We didn't use anything fancy here. This is just Lagrange duality for this. It's not immediately clear that these two are intimately connected, these two SDPs. By the way, this is an SDP in so-called equality form. And depending on a person's background, they'll either think of this one as the primal and this one as the dual, or this one is the primal and this is the dual. So I think if you work in optimization, this is the primal and that's the dual. If you work in control or signal processing, that's the primal and that's the dual. But these are just, obviously it's symmetric. Okay, so we will quit here. This actually finishes essentially all the base theory for the class. We're done. Now we'll do a lot of applications and stuff like that.